Greetings and welcome to the study. Let's solve this problem before we proceed with our video. Consider the reaction 3A plus 4B gives 2C plus D. Enthalpy of formation of A, B and D are given to be minus 25, minus 10 and minus 5 kilojoules respectively. And the heat of the above reaction is given to be minus 100 kilojoule per mole of A reactant. Find the enthalpy of formation of C. Now, the first thing that they have given is the heat of the above reaction, or the enthalpy of the above reaction is given to be minus 100 kilojoule per mole of A reacted, right? They have given the enthalpy of reaction as minus 100 kilojoule per mole of A reacted. Now, in the above reaction, there are 3 moles of A reacting. All right, there are 3 moles of A reacting, implies the net enthalpy of reaction is going to be minus 100 into 3. That is moles of A reactor. So that's going to be minus 300 kilojoules. All right. So net enthalpy of the reaction is given to be minus 300 kilojoules. So enthalpy of this particular reaction is given to be minus 300 kilojoules. All right. This is basically the heat. And over here, this negative sign indicates that this is an exothermic reaction. So since this is an exothermic reaction, so 300 kilojoules of heat is going to be released when 3 moles of A react with 4 moles of B. Okay, so this is the first thing that we have done. Next, we have to find the enthalpy of formation of C. All right, we have to find the enthalpy of formation of C. So by the definition of heat of the reaction, we have delta HR, net delta HR is equal to HP minus HR. HP is going to be 2 into enthalpy of formation of C plus 1 into enthalpy of formation of D. And enthalpy of reactants is going to be 3 into enthalpy of formation of A plus 4 into enthalpy of formation of B. Here also you can write HC and HD. HC and HD, right? So we've got the enthalpy of flux and the enthalpy of reactants. So when we put all of these in the equation over here, so we'll get minus 300, which is the enthalpy of the reaction, is equal to 2 into enthalpy of formation of C, which is not known, plus 1 into enthalpy of formation of D, which is minus 5 kilojoules, minus 3 into enthalpy of formation of A, which is minus 25, minus 4 into enthalpy of formation of B. So basically it's in a bracket over here, like this, right? So we've got this. So from here, we'll get HC. If we solve all this, we'll get HC is equal to minus 205 kilojoules. So this is the enthalpy of formation of C. All right, the enthalpy of formation of C in this case, it's going to be minus 205 kilojoules. Now, we are going to deal with Hess's law of constant heat summation. So, when we are talking about Hess's law, this is a very important law, which is very helpful in determining the enthalpy of a particular reaction. It is a very helpful, a very useful law. So the law states that the enthalpy change in a chemical reaction is the same whether the reaction takes place in one step or in multiple steps. All right. The meaning of this particular law can be very easily explained. So for example, we have to find the heat of the reaction A to D. Okay, this is a single step reaction. All right, this is a single step reaction. Okay, so let's say the heat of this reaction is H. The heat of this particular reaction is H. All right, so this, if we want to form D using A, then this is in a single step. But let's say that we are not using a single step. We are going through various steps. For example, first we are forming B. From A, we are forming B. And the enthalpy of this particular reaction is H1. Then from B, we are forming C. Enthalpy of this particular reaction is H2. And finally, from C, we are forming D. And enthalpy of this particular reaction is H3. So if you see over here, this reaction that took place in a single step, we have divided it into 1, 2, and 3 steps, right? So when we add all of them, then that is going to be equal to the enthalpy of this single step reaction. All right. So basically, when we add all these steps, we'll get this particular reaction, and the enthalpy as well would be added. So keep in mind that if we have a particular reaction, all right, if we have a particular reaction and we are given various constituent reactions for the same, then in that case, we can simply find the heat of the reaction for that particular reaction using Hess's law. All right. For example, let's say I have a reaction. A gives 3C. This is my reaction, and the heat of the reaction is H. And I have other constituent reactions. For example, I have one reaction which states 2A gives B, and the second reaction is that B, let's say B gives, or okay, let's say, yeah, B gives 6, suppose something like that. All right, we have something like this, and the enthalpy of this particular reaction is H1, and the enthalpy of this particular reaction is H2. All right, and we need to find H in terms of H1 and H2. So what our main objective would be? The main objective would be to obtain this reaction, this reaction using this as well as this equation. All right, that would be the main objective. So this is known as our aim equation. All right, this is known as our aim equation, and these are our constituent reactions. So we have to somehow manipulate these two reactions so that we can eliminate this middleman B. All right, we can eliminate this middleman B, and we can obtain this particular reaction simply. All right, so what we can simply do is we can add these two. So let's say this is reaction number 1 and this is reaction number 2. So if we add 1 and 2, then in that case, we'll get 2A gives B, and we'll add B. So we'll add this reaction. So in that case, plus B gives 6C. So over here, the reaction becomes 2A plus B gives B plus 6C. Now it's like a simple, just like a mathematical equation. All right. So if there is 1B here, 1B here, just like you would deal with variables, similarly you have to deal with chemicals. All right. So we can simply cancel off this B. Just like if you have an equation x plus y is equal to x plus 3z. So you can simply cancel off x and x. So same thing we have done over here. We have just cancelled out B. So the equation that we have got is 2A gives 6C. All right. And remember, whatever we have done to the equations, we are going to do the same thing to their enthalpies as well. So if we have added equation number 1 and equation number 2, we are also going to add their enthalpies. So the enthalpy of this particular reaction is going to be H1 plus H2. All right. By adding these two equations, we have got this reaction. So by adding these two enthalpies, we'll get the enthalpy of this reaction. All right. However, our aim equation is A gives 3C. So what we can do is, let's call it equation number 3. So what we are going to do is, we are going to divide our equation number 3 by 2. So when we divide our equation number 3 by 2, so we'll get A gives 6 by 2C, which is 3C. And that is our required equation. And as I said, that whatever we are doing with the reaction or whatever we are doing with the equation, we are going to do the same thing with enthalpies. The enthalpy of reaction also will get divided by 2. All right, the enthalpy of the reaction will also get divided by 2. So this is the heat of the reaction. All right, this is the heat of this particular reaction. So we have H is equal to H1 plus H2 by 2. That is the result of this particular reaction. All right, that is the result of this particular reaction. Let's consider another example. So let's say we have 6A plus 5B gives 2C plus 8D. All right, this is our aim equation. This is our aim equation. And we have to, we have the constituent equations. That is A gives C, B gives 2D. Then in that case, we also have 5A gives D. So these are our 4 equations, and the heat of each of the equations is given by H1, H2, H3, and H4. And we are supposed to calculate the heat of this particular reaction. All right, the aim equation. You have to calculate the heat of the aim equation. All right. So what we have to do is that we have to manipulate all these 4 equations in order to somehow get the aim equation, right? So if you see, we need 6A over here, and 6A can be obtained by adding equation number 3 and equation number 1. So if we simply add equation number 3 and equation number 1, so we'll get 6A gives C plus D. That is, and the heat of the equation is going to be H1 plus H3, because whatever we are doing the same thing with the heat of the reactions, right? So this is the heat of the reaction. All right. Now we need 5B over here. So we are going to multiply equation number 2 by 5, and we are going to add it to this equation, right? So let's call it equation number 5. So we'll do 5, equation number 5 plus 5 into equation number 2. All right. So when we do that, we have equation number 5 as 6A gives C plus D. And then we have 5 into equation number 2. So on the LHS, we'll have 5B. And on the RHS, we are going to have 5 into 2, that is 10D plus D. That altogether gives you 11D. All right, so this is equation number 6. And the heat of the reaction is H1 plus H3, that is heat of this reaction, plus 5H2. All right, 5, because we have multiplied equation number 2 by 5 and then added. So we have to multiply the heat by 5 and then add. And then finally, we have got the LHS, but we have not got the RHS of this reaction, right? So in order to obtain the RHS, we have to do something. We have to manipulate the 4th equation in some way in order to get the RHS. So if we subtract, since over here we have seen the LHS and C is not in the LHS, C is only in the RHS. So we have to subtract. So if we subtract equation number 6 and equation number 4, so we'll get 6A plus 5B minus C gives you C plus 11D minus 3, right? And as I told you, equations can be solved the same way you solve a mathematical equation. So we'll just take this C towards the RHS and add it. So we'll get 6A plus 5b gives 2c, and 11d minus 3d becomes 8d. All right. And what we have done to this, we have subtracted equation number 4. So the same thing we are going to do with the heat as well. So H1 plus H3 plus 5H2 minus H4. That is the heat of the aim equation. All right. That is the heat of this particular reaction. So hope you people are now clear on how to apply Hess's. Right? Hope you can understand how to apply Hess's law. So now we are going to solve this particular problem, which is quite similar. We now know how to deal with it. So we have to calculate the heat of formation of methane gas from the following combustion data. All right. So these are the equations that are given to us. Now, first of all, we have to identify our aim equation. Okay. So first of all, let's identify our aim equation. So it's heat formation of methane. So carbon plus 2 hydrogen, carbon solid, hydrogen gas gives us CH4. This is the aim equation. Remember, we have to find the heat of formation. So this should have the coefficient as 1. It should be 1, right? And we have to find this H. Okay. And the aim equation, the other constituent equations that are given to us are CH4 plus 2O2 gives CO2 plus 2H2. Just a minute. CH4 plus, that is the combustion of methane. All right. Over here, they have directly given us the heat of combustion of methane. They might not actually give us this data. Instead, they could have simply said that the standard heat of combustion of methane is given to be this. So we should know that this is the reaction for heat of combustion of methane. All right. So anyways, they have given the equation right now. So it's not a difficult question anymore. So it's going to be CO2 plus 2H2. This is our first equation, the heat of the reaction being H1. All right. And the second equation is C plus O2 gives CO2. That is the second equation. And the third equation is H2 plus half O2 gives H2O. This is our third equation, H3. All right. So now we have to obtain our aim equation. This is our aim equation. We have to obtain our aim equation using the constituent equations. All right. We have to obtain the aim equation using the constituent equation. So we have to eliminate CO2 and water. Right. So we can actually clearly see what we actually have to do. But then again, first thing, we need carbon and hydrogen on the LHS. So with equation number 2 and equation number 3, we are simply going to add. We cannot subtract equation number 2 and equation number 3. Second thing, we need CH4 towards the RHS. So for equation number 1, we'll have to subtract. We'll have to subtract equation number 1 somehow in order to get CH4 towards the RHS. So remember that whatever we are going to do, we could multiply something or we could divide something, but this has to be followed. We can only add equation number 2 and 3 and we can only subtract 1. Why? Because we need carbon and hydrogen towards the LHS while we need methane towards the RHS. All right. So in order to take methane towards the RHS, we'll have to subtract equation number 1. Now, second thing, the coefficient of carbon is 1. So for equation number 2, we are only going to multiply it by 1. However, the coefficient of hydrogen is 2. So in equation number 3, the coefficient of hydrogen is 1. So we'll have to multiply this entire equation by 2. So we are going to multiply equation number 3 by 2. And then there is no other change. right? There is no other cheese. So this is going to be done. Let's once do this and see if we get the aim equation. So what we are going to do, we are going to multiply equation number 2 by 1. So we'll get C plus O2 gives CO2. This is being added. Okay. Then we have the second equation, which we are multiplying by 3. So, sorry, we have the third equation. We have the third equation, which we are multiplying by 2. So it is going to be 2H2 plus O2 gives 2H2O. Okay. And this is also being added. And finally, we have the third equation. We have the first equation, which is being subtracted. So we'll have CH4 plus 2O2 gives CO2 plus 2H2. And this is being subtracted. All right. So when we solve all these, then we are going to get C plus 2H2 plus oxygen gives 2 oxygen minus CH4 minus 2O2, right? So as a mathematical equation, we have to solve it. So this and this gets cancelled. Then over here on the RHS, we are going to do CO2 plus 2H2O minus CO2 minus 2H2. So these are going to get cancelled. All right. And then again, this is in negative, so we can send it towards the RHS. So we have got the aim equation, C plus 2H2 gives CH4. Right, this is the aim equation that we have got by doing this particular calculation. So the same thing is going to happen with heats as well. So for second equation, we are going to multiply heat by 1. So 1 into H2. Then for third equation, we are going to multiply heat by 2 plus 2 into H3 minus H1. So that is the heat of this particular reaction. Now we'll go and find the data. So we have H2 plus 2H3 minus H1. So the heat of formation is going to be H2 is minus 393.78, H3 is minus 286.03, and H1 is minus 890.94. When we substitute these values, we are directly going to get the result as minus 74.9 kilojoules. I have done this entire question too much in detail. I have solved each and every step very slowly. But once you practice, once you're able to do questions like these easily, then in that case, this is hardly going to take much time. You just have to form these equations, form the aim equation using constituents, and you have to algebraically multiply and multiply, divide, add, subtract the heats as well. So based on that, you will be able to get heat of the reaction easily.